Hello everyone, welcome back to Bamane Pharm lectures, where we make pharmacy simple. Our today's discussion is question and answer discussion. Remember, every Friday we have question and answer discussion, so feel free every Friday to check out for videos concerning all questions in pharmaceutics, either pharmaceutics 4, either pharmaceutics 1, either pharmaceutics 3, even for CPH. Every Friday we have question and answer. You can always feel free to ask any question, to comment with your question. I'll always consider those questions in the next discussions, such that you can be able to learn and gain confidence, so that you can be well equipped when it comes to any laboratory, pharmaceutical practical, or any theory paper. So today our focus is mainly about what we have been covering in the previous lectures. And we have two questions to answer. These are purely UHPAB questions I picked directly from those papers, so that we can review what exactly takes up there, so that you can have or increase on your question approach, so that by the time it comes an exam, you'll go to Excel to get an A pharmaceutics. It is very easy. Let's start off. An ophthalmologist is treating one of his patients for an eye infection. The ophthalmologist prescribes 60 mils. The doctor prescribes 60 mils of 2.5% weight in volume amikacin sulfate isotonic solution, and they are supposed to give 2 drops in affected eye every 2 hours. But amikacin sulfate has a molecular weight of 781.76, and it is an amino glycoside type of antibiotic, which we very well know when we refer to our pharmacology. And when it is dissolved in water, it decomposes to produce 3 ions. The first question, determining the weight in milligrams of amikacin sulfate needed to prepare the solution, 4 marks. So, our first question, we need to determine how much of amikacin sulfate was to be used in this prescription. Remember, they have told us that the volume required is 60 mils. But what we know is the percentage strength, which is 25 grams per 100 mils. Remember, every time we say 2.5%, we mean that we have 2.5 grams of amikacin sulfate in 100 mils of the solution. So, if you have 2.5 in 100, how about the 60? It will give us the weight of amikacin that we need. So, we shall say if 100 mils of the solution contain 2.5 grams of amikacin sulfate, how about the 60 mils? It will contain 2.5 divided by 100 times 60. This will be in grams. So 2.5 divided by 100 times 60, we shall get 1.5 grams of amikacin sulfate. So this is the weight of amikacin that is required in 60 mils, and that is our part A of the question. Part B, they are asking us to calculate the sodium chloride equivalent of amikacin. And they have given us the I value of sodium chloride and also that of amikacin chloride, amikacin sulfate, which is 2.6 because it produces 3 ions. So, but we know from our formula that sodium chloride equivalent or E value of amikacin is given by 1 molecular weight of sodium chloride, because it is what we are going to use as our isotonicity modifier, divided by high value of sodium chloride times high value of amikacin, divided by molecular weight of amikacin. So, when we substitute this, you will realize that the molecular weight of sodium chloride is 58.5 divided by its high value, which is 1.8, times high value of amikacin is 2.6 divided by its molecular weight, which has been given to us as 781.76. And when we compute this, we shall have 58.5 divided by 1.8 times 2.6 divided by 781.76, and when we compute this, we shall get 0.108 as the sodium chloride equivalent of amikacin. So, after obtaining the sodium chloride equivalent of amikacin, our next question, they are asking to calculate the amount of sodium chloride needed to make the solution isotonic. Remember, when we are doing that, the first step we say is to identify what are we using as our isotonicity modifier. In this case, it is sodium chloride. So if it is called sodium chloride, we know that it is only 0.9% sodium chloride that is isotonic with blood plasma or lacrimal secretions. So we are going to determine the amount of sodium chloride in 60 mils of the question. So this will be equal to 0.9 divided by 100 times 60. And when we compute that, we shall have 0.9 divided by 100 times 60. This gives us 0.54 grams of sodium chloride. So this is the amount of sodium chloride that we need. But our question, we need to make this solution isotonic. So we are going to also obtain the sodium chloride equivalent. The sodium chloride equivalent of amikacin sulfate, which is equal to the product of, that is product of now amikacin. We look at the sodium chloride equivalent of amikacin, which has been given in this case. So what are we going to do? We know the mass of sodium chloride equivalent and also that of amikacin sulfate. So we shall get the sodium chloride equivalent of amikacin, which is 0.108 times the weight of amikacin sulfate, which we have already obtained here as 1.5 So when we multiply that, we shall have 0.108 times 1.5. And this will give us 0.16 grams. So this is the sodium chloride equivalent of amikacin sulfate. But remember, to make the solution isotonic, the amount should be this. But on this amount, we already have 0.16. So that means that the remainder is going to be provided with our isotonicity modifier. So that means the remainder will give us the amount of sodium chloride to be added. So that will be the difference between the total amount of sodium chloride required in the 60 mils minus what we already have, which is 0.16. And when we subtract this, we shall have 0.54 minus the 0.16. And when we compute this, we shall get 0.38 grams of sodium chloride. So this is the amount of sodium chloride that is required to render this solution isotonic. So that means if we are producing our final product formula, it is going to be amikacin sulfate, sodium chloride, then water for injection. Amikacin sulfate, we have obtained it as 1.5 grams. We also now know the mass of sodium chloride as 0.38. But water for injection will add up to 60 mils, and that will be our working formula. Let's look at our part D of the question. Part D is saying, I hope you have put this down. Part D says, how many milliliters? So we are looking for mils of 23.5%. Remember, if they say 23.5%, we mean we have 23.5 grams of sodium chloride in 100 mils of the solution. So, they are asking us how many milliliters of 23.5% sodium chloride injection should be used to obtain the required sodium chloride. But remember, we already said that if 23.5 grams of sodium chloride is contained in 100 mils, how about the amount that we know? So, therefore, the 0.38 grams of sodium chloride will be contained in 100 divided by 23.5 times 0.38. And when we compute this, we shall have 100 divided by 23.5 times 0.38. And when we compute this, we shall have roughly 1.62 mils, which is approximately 1.6 mils. So that means we need 1.6 mils of this solution. So if we are using a solution of this concentration, that means in that case, instead of having the mass of sodium chloride, we shall simply have 1.6 mils of sodium chloride, then water for injection, add up to 60 mils. And that is how we attempt a question of that nature. I hope you are at the same pace with me. Let's look at our next question and answer question. So, in our second question, a hospital pharmacist fills a medication order calling for an intravenous fluid of dextrose 5% in a 0.9% sodium chloride injection and 40 milliequivalents of potassium chloride in a total volume of 1,000 mils. The intravenous infusion is administered through an IV set that delivers 15 drops per mil. With such question is, you read as you summarize, and this is milliequivalents, a topic we covered. So you need to test your skills and see, have you really mastered milliequivalents? Can you really answer any question? So you can even feel free to pause this video and try out this question, and then you check back and see whether you can get the same answer with me. Let's pay a very keen attention as I take you through this. Through a giving set that delivers 15 drops per mil, they have given us the drop factor. Drop factor as 15 drops per mil. The infusion has been running at a rate of 12 drops per minute. So they have given us the flow rate. Flow rate is another topic that we are going to cover, and don't miss it out anytime from now. 12 drops per minute, and this runs for 15 hours. Then during the 15-hour period, how many milliequivalents of potassium chloride have been administered? So that means they want us to find the milliequivalents of potassium chloride that has been administered. But remember, we need to know how much volume of potassium chloride was delivered or administered in 15 hours. That is the first guiding aspect of it. After you obtaining the volume of the solution that was administered in 15 minutes, in 15 hours, then we shall be able to know the amount of potassium chloride that is in that volume. Remember here they just simply told us that the 40 milliequivalent is in 1,000, but not all this 1,000 was delivered or administered to the patient according to our IV set, which delivers 15 drops per mil for 15 minutes. So we need to find out. So we need to obtain the volume that was administered, whereby we shall start from this point. We know very well we shall first convert the 15 hours to minutes. We know that 1 minute, 1 hour is equivalent to 60 minutes. How about the 15 hours? This will be equivalent to 60 times 15, which gives us 60 times 15. This gives us 900 minutes. So, if you have 900 minutes, if the flow rate is 12 drops per minute, how many drops will be in the 900 minutes? So we shall say that 1 minute has 12 drops. How about the 900 minutes? It will have 12 times 900, and when we compute this, we are going to have 10,800 drops. So we have 10,800 drops in the 900 minutes, which is equivalent to 15 hours. So after obtaining that, remember we know from our drop factor, we know that 1 mil, we know that 15 drops are equivalent to 1 mil. How about the 10,800 drops will be equal to 1 out of 15 times 10,800. And when we compute that, we are going to get 720 mils. So, this is the volume of the solution that was administered in 15 minutes. Or else, another person may prefer to use the shortcut or the formula, whereby we know that flow rate is equal to volume times drop factor divided by time, which in this case it is in minutes. So we know that flow rate has 12, which is equal to the volume we are looking for times drop factor, which is 15, divided by the time which we have gotten as 900 minutes. So our volume will be equal to 12 times 900 divided by 15, which will still give us 720 mils. We are going to cover the topic of flow rate in the next lectures, so don't miss it out. You will know when it is out. So after obtaining now the volume of the solution that was delivered in 15 minutes, we are now going to say that if 1,000 mils of the solution contain 40 mil equivalents of potassium chloride from our question, 40 mil equivalents of potassium chloride in a total volume of 1,000 mils. How about the 720 mils? It will contain 40 divided by 1,000 times 720. And when we compute that, we shall have 40 divided by 1,000 times 720, and this will give us 28.80 mil equivalents. So this is the amount of mil equivalents that was delivered in the 15 hours. That is our question 1. I hope you are at the same pace with me. Let's look at our next Roman. They're asking how many milligrams, how many grams of potassium chloride have been administered. But we know that one mil equivalent each of potassium and chloride ions is contained in 74.5 milligrams. If we can recall from our previous lecture, where we say that equivalent weight of potassium chloride is equal to molecular weight of potassium chloride, which is 74.5 divided by values, where we shall get 74.5 grams, its unit is grams. Then 1 mil equivalent of potassium chloride is equal to 1 out of 1,000 from the definition of equivalent weight. I mean from the definition of mil equivalent times its equivalent weight. So when we say 1,000, 1 out of 1,000 times the 74.5, this gives us 0.0745. But remember, it should be in milligrams from our definition. So when we multiply this by 1,000, we shall get 74.5 milligrams. So this is where I'm deriving this relationship. If 1 mil equivalent each of potassium and chloride ions is contained in 74.5 milligrams. I hope we are moving together. How about the 28.8 mil equivalents that was delivered? This will contain 74.5 times 28.8 divided by 1. The answer is in milligrams. So this is going to be 74.5 times 28.8. This will give us 2,145.6. And when we convert this to grams, it will be 2.1456 grams. We simply just divide by 1,000. So this is the amount of potassium chloride that was delivered in 15 minutes. Let's first go to part C. How many millimoles of potassium chloride have been administered? Still we are in the same volume. But remember, we said that milli equivalent is equal to millimole times variance. So that means we shall say millimole will be equal to milli equivalent divided by variance. But remember, we know the amount of potassium chloride that was delivered in 15 hours as 28.8 milli equivalents divided by 1. So this will still give us 28.80 millimole. So the number of millimoles of potassium chloride is 28.8 because we know that for compounds that have got one variance, 1 millimole is equivalent to 1 milli equivalent. As we looked at the relationship between those two. Let's look at our last Roman, that is Roman D. So, in Roman D, we are going to say, I hope you have put this down. In Roman D, they want the total osmolarity of the intravenous fluid. Remember, when they say total osmolarity, osmolarity is always calculated in liters. So, that means we are going to get the osmolarity of potassium chloride, where we know that we have 40 milli equivalents in a liter. So if we have 40 milli equivalents in a liter, we know that 1 millimole per liter is given by millimole being multiplied by number of particles. So that means what we are going to do, we are going to get the millimoles of potassium chloride. But remember, since potassium chloride has got one valence, that means that we also have 40 millimoles of potassium chloride being multiplied by 2, because we know potassium chloride dissociates to produce potassium ion plus chloride ion. So we have 2 particles. So when we multiply this, we shall have 80 millimoles per liter. So our next step, we are going to look at sodium chloride. But remember, we know the 0.9. So we are going to get the amount of sodium chloride in 1 liter. So we shall say if 0.9 is in 100, how about the 1 liter? So the 1 liter will be 9 grams per liter. But remember, from our formula for osmolarity, we say that millimole per liter is given by concentration in grams per liter divided by molecular weight times I value being multiplied by 1,000. We multiply by 1,000 to convert osmo to mosmo. So that means we are going to say our mass of sodium chloride has already been given. So what we are going to do, we are going to write it. This is 9 divided by molecular weight. Molecular weight of sodium chloride is 58.8 times high value. High value is the number of particles. Sodium chloride also dissociates to produce two particles, where we know that we shall get the sodium ion plus chloride ion. So this plus this, we get 2 times 1,000. And when we compute this, we are going to have 9 divided by 58.5 times 2 times 1,000. We shall have approximately 308 mosmol per liter of sodium chloride. Our next thing is dextrose. So mosmol for dextrose per liter will also be equal to the mass of dextrose. They have given us the one in 100 mils. So we shall say 5 divided by 100 times 1,000. We are going to get 50 grams per liter of dextrose. So we are going to say 50, which is in a liter, divided by the molecular weight of dextrose is 180. So divided by 180 times 1, because we know dextrose is a non-electrolyte, being multiplied by 1,000. So when we compute this, we shall have 50 divided by 180 times 1,000. This will give us approximately 278 mosmol of dextrose. So the total, therefore, total mosmol per liter is going to be now the 80 plus the 80 for potassium chloride plus the 308 for sodium chloride plus the 278 for dextrose. This will give us 80 plus 308 plus 278. This will give us approximately 666 mosmols. And that can tell you that this solution is hyperosmotic because it is greater than the average range of the normal serum milliosmoles. And that is how we attack such a question. It was also a UHPAB question. So please, every Friday we have a question and answer discussion. Feel free to be at home and learn at Bamane Pharm lectures, where we can solve the hardest calculations in the simplest way that you can understand. Please, if you find this video very useful, don't forget to like, to share the channel with your colleagues and other students out there who may be seeking for knowledge to excel in their pharmaceutical practicals and as well their practicals. And also don't forget to subscribe to the channel so that you can keep the channel growing, so that thousands of students out there, they can discover the channel and learn, so that we can all excel and make pharmacy simple. Let's meet up in the next lecture, and don't forget next Friday we shall also have a question and answer discussion about the topics being covered at Bamane Pharm lectures. Let's meet up in the next lecture. Thank you for watching.